Alright, so here we go. Pay attention, I don't have time. Tick tock, tick tock. Okay, look. Here's what we've already talked about, and you might want to write this down on a separate sheet of paper. Okay? On the left side, I want to talk about something called gravity. Gravity is very bizarre, and it's basically a force that exists between everything that has mass. So this is all based on this fundamental property of matter called mass. And there turns out the first basic equation we have, we talk about an object's weight. And we're just like, oh, that's just m times little g, right? And we said on Earth, little g is 9.8 about meters per second squared. Well, what the heck? Where does that little g come from? This equation, which we call weight, came from the universal law of gravitation, which I write with a capital G down here, which equals negative G M, and I'm going to say for the Earth, M1, that's the mass of any object, okay, times ME divided by RE squared, okay? And then I'll go ahead and put a little R hat on this just to top it off with our little vector notation. I could even have vectors up here as well. So what this says, okay, it looks like it spells gimme. Give me the answer. This is a constant. Right? Constant. And basically it says that the force of gravity that exists between any two objects that have mass, or in this particular case, between an object and the Earth, okay, the mass of the object times the mass of the Earth divided by the radius of the Earth squared. Why the radius of the Earth? Because most objects are pretty close to the surface of the Earth. And even if you are on the top of Mount Everest, you are only about 6 miles up in the air. Okay, right? You follow me? The radius to the center of the Earth is 4,000 miles, más o menos. Okay? That means adding like 6 extra miles by climbing Mount Everest, big freaking deal. The difference between 4,000 and 4,006, who cares? Okay, so we just approximate your distance from the center of the Earth to be the radius of the Earth. Okay? And so when you combine these things together, okay, that's where we spit out this idea. And up here, I'm going to add a little subscript 1, because that's that M1 right there. So let me rewrite this, okay? F little capital G equals M1 times, and I'm just going to look at the magnitude of this, so let me ignore that negative sign for a second, okay? I'm ignoring the negative sign. Times GME divided by RE squared. Okay, and I'm also ignoring that. I'm just talking about magnitude here. Okay? That shows us that little thing here, that's little g. Okay? So GE, not General Electric. Gravitational acceleration due to the mass of the Earth is GME, and again, just talking magnitude, divided by RE squared. Okay, this is the magnitude of the acceleration due to Earth's gravity. Okay? One other just key feature of this law is that, boom, it's always attracts. Okay? Always attracts, right? Lizzie, question.
So you know those like top atmosphere skydivers?
Yeah.
Are they far away enough from the Earth to like change their gravitational like attraction?
Yes. How high did Felix Baumgartner skydive from? How many miles up?
12 down.
It wasn't that far. It was far. It was like many miles up, right?
14 miles.
Something. But yeah, his gravity would be slightly different, but not by much, because 14 miles is still not that significant compared to the radius of the Earth. Right? You get what I'm saying?
Yeah.
Yeah, so even in the International Space Station, which is in free fall, like Earth's gravitational pull is very significant. I mean, the moon is orbiting the Earth because of this force of gravitational attraction between the Earth and the moon. So that still, matters a lot. Despite the fact that this is a very weak force, and in fact, maybe we'll write this down too, right? We said before, G equals 6.67 times 10 to the negative 11 newtons times meters squared divided by kilograms squared. The units, this is a proportionality constant, right? It's very tiny, negative 11. However, the mass of the Earth, it's about 10 to the power of 24 kilograms. So it's enough to overcome that very tiny gravitational constant here. Yeah, Lizzie.
So you're saying on the moon, is it the moon's attraction to the Earth is still 9.8?
No, good question. No, I wouldn't use that because the moon is about 220,000 miles away. So the moon, that's more than our 4,000 mile. So I would definitely use a different. I would not try to use 9.8. Okay, anything cosmically you would recalculate using Newton's universal law of gravitation. My point is that we're just used to writing it this way, right? M times G. So what do we call this little g? This little g acts like, and this is the main point here, okay? Little g represents the Earth's gravitational field. Okay, which is this, boom, right here. Okay, written that way. The Earth's gravitational field. It's what causes mass to accelerate. Okay? Savvy? This is really important. Now, let's look at what we have on the other side here. We have electrostatics. Electrostatics depends on a fundamental property of matter called charge. Okay? And we are going to introduce a very basic force that's going to look like this. Fe equals, and really I could say, I would write it like this. I'd write it like over here, 1 and E maybe. And what this says, it's a gravitational force between mass 1, whatever it might be, and the Earth. So down here, I'm going to write this one. We don't really talk about the electrostatic attraction of the Earth, but let's just talk about between any two charges, 1 and 2. Okay? Just like I had 1 and Earth, I have 1 and 2. And this is, and I'll even add underneath this, I'll add G with a little E, because we know that's what it is. We've just never taken the time to add that in, but we know we've always been talking about Earth. So, how does the analogy go? The force of electrostatics between two charges would be Q1, that is in the electric field of the second charge. Okay, so there's this very direct parallel. Instead of mass times some gravitational field, we've got Q times some electric field. Okay? So E stands for electric field. And we'll even say the units of electric field, you could figure it out just by thinking about a little dimensional analysis. When we multiply electric field by charge, what's charge measured in? What's charge measured in? Coulombs. When we multiply it by coulombs, we need to get newtons. So that electric field is measured in newtons per coulomb. Okay? Now, where does this equation come from? It comes from the more fundamental and basic Coulomb's law, which says F with a little e between 1 and 2 is equal to K, Q1, Q2, the product of the charges, divided by the distance between them squared, R hat, directly along their centers. Okay? So, let's rewrite this. Fe 2 equals, I'm just going to bring the Q to the outside, Q1, and whatever's left behind, K, Q2 over R 2 squared Okay, actually, let's talk about magnitude now for a second. Just like I did over here. And we say that this thing, compare our top line here. Let's put equation A to B, C, I'm just labeling this. Compare equation C to equation A, right? So what's this thing in parentheses? That's the electric field. Electric field, which is a vector, okay? Which I'm going to write it this way. K Q2 over R12 squared R hat. Okay? This right here, and I'm going to write out. This is the electric field at some position called 1, because I have R12, that's what that 1 is. At some position 1, caused by charge at position 2. Okay? Here's the tricky part, though. It's a vector, and the tricky part is that the rule, okay? The rule about the direction. The E field, and I know we just wrote this on the previous page, but I'll write it one more time. Always shows its effect on a positive test charge. So you'll put a little tiny positive there. Writing all this down. The E field always shows its effect on a positive test charge, okay, which means, bottom line, the E field points away from positive charges and toward negative charges. Okay? The electric field points away from positive charges and toward negative charges. I have a couple of simulations that draw electric fields that I will show you. So, really quickly, over here, you see this is a charge of -1, and you see the arrows are pointing toward it anywhere in space. This is the idea. A charge occupies some space. And what it does is it warps and it changes the entire space around it. These vectors are pointing directly toward that charge. Notice that the vectors are longer the closer they are. The field is stronger closer to the charge. It's an inverse square law. So if you are twice as far away, the field is only 1/4 as strong. If you are 3 times as far away, the field is only 1/9 as strong as it used to be. If I change the magnitude of this charge, I don't know if that did anything. Oh, add, uh-oh, now they're bouncing around. Pause. 2 charges. Okay, right in between them, they might cancel. I don't know if I can move them. Yeah, look at this. Look at right there in the middle of them. They're creating, it's kind of canceling out. The 2 arrows are pointing directly towards each other. Okay. And you see that they're both negative. Let's change, let me hit reset. Reset all settings. Add a charge. This one's -2. see if I can make one positive 2. Oh, whoa, 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 whoa. Hey, lovebirds, get a room. So you see how they, can you tell which one's positive and which one's negative?
Yes.
Which one's positive, which one's negative? The one on the top is positive, the arrows point away from it. And the one on the bottom is negative. When I hit play, you kind of just, whoa, see how it plays out, which is kind of interesting. Where is sticking away? Okay. If you look at the way that the field is shaped, look at this distance out here. Or look at this one. Actually, let me just move these around because I want to show you this. That one's positive, that one's negative. So here's the thing, you guys. I asked you on your warm-up, and I'm going to flip back and show you the warm-up again. On your warm-up, I asked you, look at this point right here. What's the direction of the electric field up here at this point? It's to the right. You see that? It's not too large, but it's to the right. Now look back at your warm-up, the first page of your warm-up, what you did here. Okay, and I just want to show you that we've only drawn the electric field at one particular point. But in actuality, the electric field is established everywhere. And what does it look like when you have 2 point charges like this? Well, everywhere it's pointing away from the positive and into the negative charge like that. The electric field's actually everywhere. And it's pointing like that, and when it comes up here, it goes like that. And we were just zooming in and looking at one particular point of the electric field. Okay? I hope that makes sense to you. Okay? I will show you one other simulation that's cooler. You guys actually mess with this your freshman year without much understanding, I think, of electric fields. I just placed a charge, okay? This charge right here is a positive 1. I don't like this simulation. It's a good simulation, but it doesn't show the direction of the field lines, which I really don't like. I just wish that it had that. It would be great. And so these are positive charges. If I drop one in that has, say, a larger positive charge right here, you can see that it has more field lines coming out of it. That's to indicate its strength. If you are drawing an electric field, that's usually what we do. The more lines that come out of something, the stronger the charge is. They're both positive. These field lines do not cross. This is making a map of space. I'm going to explain what the red circular lines are in a second. But basically what would happen is if you dropped a little positive charge here, imagine like a 3-dimensional topographical map. Okay? If you dropped a little positive charge right there, it would follow this line and fly out just like that. That's what these lines show you. Now, just because there's only 5 lines coming out of this, it doesn't mean that right here there's no electric field. There definitely is. We just can't draw lines everywhere, and you wouldn't be able to see anything. You understand what I'm saying? There's still an electric field right here. It still points away from that. This is just a way to visualize the difference in strength of charge. Okay? It would be better to think somehow about the multiple lines here as steepness. This would be like a very tall mountain coming out. Okay? This would be a shorter little tiny hill coming out. And a ball rolling down the hill would be like a small positive test charge. You place it right here, it's going to shoot down the hill faster because it's very steep. In fact, the red lines in this simulation are called equipotential lines. And it has to do with something called voltage, okay? Which we will talk about in a minute. It has to do with energy. And the way that you can think about these red lines is actually on a real topographic map that shows you different elevations or altitudes. Okay, the circles close to the center here are at the highest elevation, and they drop lower and lower. And the circles, one full circle means you were at the exact same elevation. Okay, I don't know if you guys have. I know some of you guys have gone like hiking before, and you've probably looked at topographic maps. And the lines connect an area where the height is all the same. And what that means here is basically the energy level is the same at any point along this equipotential line. Okay? It's like, you can kind of think of it as like equal potential energy. Okay? Joseph.
Does the brightness of those lines actually matter too? Because some of them are dimmer than the other.
Yeah, definitely. I think the brightness indicates kind of like the strength of it maybe, but I don't know actually, because this is like very dark, so it might have to do with like the lowest point. That's a good question. It's hard to see like a good pattern. It definitely looks weaker out over here, closer in the middle near the top. Yeah, I think it has to do with the strength of those lines. But it is kind of a weird space right there in between. All right, so let me just show you really quickly what it would look like with, here's a positive charge, and let's throw a negative charge in there and see what happens. And you see the lines connect, okay? And actually, so in this case, blue indicates a negative amount of potential, okay? Which is weird to think about a negative energy. But it's sort of like, here's how you can think about it. Positive lines mean positive elevation, red lines mean positive elevation. And blue lines mean like negative elevation, like you're actually sunk in there, okay? And so, again, the lines show you what would happen. A small positive test charge would fly toward the blue. Do you have a question, Ricardo? Okay. So that's kind of this general rule about the way that electric fields are drawn. All right, so right down here, one more thing to include as an important note, okay? Electrons, or any negative charge, swim upstream against the E field. What the heck am I talking about? Electrons swim upstream against the electric field. The electric field shows us what happens to positive charges. So what do negative charges do? The exact opposite. Okay? If you guys remember what I said, I think last week before you guys took the test on thermodynamics, I said this unit is challenging for 3 reasons. The 3 reasons why this unit is particularly tough is because, 1, it's why electrostatics is harder than gravity. 1, we now care about changing force. We can no longer just say, oh, 9.8 works all the time. Not anymore. Instead, the force is changing, so the acceleration is changing. Changing force, acceleration, which means we're talking about jerk. Okay, that's one reason. 2, we are abstracting to talk about space with nothing in it. This is so weird. I just happen to have a domino here, but what we're saying literally is that here is this charged domino. Okay, it's the only thing I have here, whatever. Okay. And this charged domino, we're going to talk about not the domino itself, but the effect that this domino has on some empty space around it. Doesn't matter where this is. We're just talking about empty space. That's what the electric field is. And when you look up at this equation, we can talk about, this is talking about empty space. It's hard to think about emptiness. It's very abstract. This equation up here says, okay, so here you have a domino. Let's call this domino, I wish it had, boom. Let's call it this one, boom, 2. This is domino number 2, okay? And it's changing this space around it. And what happens when you put a second domino, domino number 1, into that space? Now you can talk about the force that is exerted on this domino number 1 when it's in the electric field of domino number 2. But even without domino number 1, we can still talk about what's happening in this space. And then we say, oh, okay, the bigger the charge you put into the space from electric field 2, the greater the force it's going to feel. Okay? So the 2 tricky parts are calculating the magnitude, right? And then figuring out the direction that it's supposed to point in. Okay? And that's what all these rules are for that we've written down. Does this make sense so far? Good, because I haven't even gotten to the hard part yet. Okay, the hard part's when we start talking about voltage and energy, which we will in a second. So 1, changing force, acceleration. 2, the abstraction to empty space. And the third thing is simply attraction and repulsion. We have 2 different directions to worry about. God, that makes it so much harder. I should probably just start this entire unit where we could say every charge is positive and make life a little bit easier, and then introduce negative charges. But instead, let's just dive right into the deep end, shall we? Why not? Okay. We're gonna do some practice problems, but I just want you to let's just talk really quickly. Some notes. I've already filled them in. This is on the second page of your warm-up. Why was the idea of a field system created in the first place? What the heck? Why are we talking about abstract things that are hard in empty space? Because action at a distance doesn't make sense. How does one domino know that it's supposed to be attracted or repelled by another domino? If they're separated, how are they possibly influencing each other? So there must be some other medium between them that's transmitting this information about forces. And so we say that that medium is space itself, which is weird because this is even true in outer space where there's nothing there. How can you warp nothingness? A charge in outer space, the sun, the gravitational mass of the sun somehow affects space. It's like space is this thing. And for, hundreds of years, people called empty space, they called it ether. Because they wanted to give it a name. It kind of sounds like heather, but it's not. It's just ether. Like they thought that maybe the cosmos is some mystical, fabric. Like if you were an astronaut floating in space and you just swept your hand through it, you could take a bite out of God somehow. Right? The cosmos itself was a real thing. And then these guys, Michelson and Morley, two old famous American physicists, about 120, 30 years ago, conducted this experiment to see if there actually was some substance in space that might change the speed of light somehow. And what they found out was that it didn't. It didn't, somehow light traveling through space wasn't slowed down. And this was an incredibly important experiment. Everybody thought, oh, okay, light should go a little more slowly. It was very instrumental to Einstein developing his theories, was this Michelson and Morley experiment. But they didn't necessarily prove that there wasn't this thing called ether. They just showed that light could travel at the same speed through it no matter what. I don't know. This is not, I told you guys to write this down before, and I'll say it again. More often than not, there's just an answer, not the answer. And so to get around this problem that we all have, scientifically with cause and effect, the fact that these two things separated somehow know that the other one exists, we create this idea of a field. And we say that one object by itself changes all the space around it. And that allows us to go to sleep at night. Okay, it's just a trick. It's a weird trick. And maybe it's terrible. And maybe you guys will go to college and you'll think really hard about this and you'll come up with a better solution to the idea that there's some modification or warping of space based on basic properties of matter, charge and mass, changing space around it. We already talked, but that's it. That's this whole idea. It is incredibly profound. Okay? And I want you to understand that it's not like someone made some important discovery about the true essence of our universe. It's just like, hey, let's just think about this. And then we don't have to worry about objects acting on each other. It'll just allow us to get sleep at night. And I don't get any sleep at night because it bothers me. So anyway, where do field lines that leave a positively charged particle end up? They go to infinity. They go to the edge of the universe. This is a very weird principle and concept. Action at a distance. Famous poet, actually famous physicist who loved poetry, I believe it was Niels Bohr, about 100 years ago. He said, and this is the idea about gravitational fields, that even the smallest mass is attracted to every other mass in the universe. He said, every time you pick a rose, you bring the stars a little closer. And what he meant was, you lift the mass up. The gravitational force between the stars and the rose is now a little bit stronger because you've lifted it up and brought it closer. There were a lot of romantic physicists back 100 years ago. They were really, pulling in the ladies. So anyway, we've talked a lot about this. How do you calculate the electric field set up by one charge at any given distance? Let's just write that in. Yes, Teresa.
So, is all of this basically like not real? Like, this is all hypothetical?
Woo! That is a question that we will discuss when we get into the philosophy of science unit. Is it real? Is science that actually is real? That's like, I don't know, a belief that you may have or may not have. I said more often than not, we have an answer instead of the answer. I don't know, maybe every once in a while we do have the answer. Okay? It kind of depends on how you want to view the world. Okay? It's your choice. So anyway, there's our, if you want to turn into a vector, you'd have to say, like, this is weird, right? There's only one charge here, so what is this distance? This distance just goes to some point in space. Okay? All right. How do you calculate the electric field? Oh boy. As if this weren't hard enough. Okay? This is just for one particle. Read this right here. How do you calculate the electric field caused by multiple particles? We use what's called the principle of superposition. That just means adding vectors. Okay, because E is a vector, it obeys the principle of superposition. To determine E caused by a set distribution of charge, like a long-charged rod, you need to use the summing properties of calculus, which is exactly what you do if you take engineering, physics, and calculus next year. Maybe we'll preview some of that this year. Let's, instead of getting into this, because this is basically, we studied forces, right? We talked about projectile motion, dropping objects in a gravitational field, right? And calculating their speed and all that stuff. Then, after that, we're like, oh, well, instead of looking at through physics problems and physical scenarios through the paradigm of forces, we could change the lens through which we look at the world and say, what about energy? And we said, okay, instead of dropping an object in a gravitational field, we can talk about potential energy that it has. And that translating into kinetic energy. Well, guess what? We're going to do the exact same thing with electrostatics next. But first, before we dive into force and energy at the same time, let's just focus on force for a minute and make sure that we can study all that stuff. So I'm going to just draw some lines there. We'll come back to 9 and 10. On the back, these are just drawing EFields. I've already shown you some, so we're going to skip that in the interest of time. These were the forces. These are the handout that I wanted to give you guys last time, and I forgot. It's mostly on Coulomb's law. We already know all this stuff. Boom. So now what we're going to do, we're going to try to put it in practice. Okay? Find the magnitude and direction. Do you want to do the hard one or the easy one? Trick question. They're all hard, suckers. Find the magnitude and direction of the electric field acting between the two charges below. The charge on the right is positive 6 microcoulombs, and the charge on the left is negative 3 microcoulombs. Okay, here's what we're going to do first. Step 1, draw vectors, just like you do for net force. Okay, so let's start. I'm going to call this side right here, I'm going to call it 1. I'm going to call this guy over here 2. I'm going to use some different colors. So right here at this point, this is the point in space we're looking at. What is the direction of the vector we should draw from the electric field caused by charge 1? What direction is it pointed?
Left.
It is pointed, does it point away from positive, or away from negative charges, or toward negative charges? Towards them. Okay, so that's going to be E1. Okay, and what about the electric field from this guy over here? Which way is it going to point? It's a positive charge, so it points away from the positive. So good news! Adding and subtracting the vectors here should be really easy. Our net electric field is just going to be the sum of the two. In fact, you know what we should just do right now, just to make sure? Give me those points. What's the angle?
180.
180 degrees. Don't say 0, point to the left. Respect the x. Okay. Step 1, draw the vectors. 2, calc magnitude of vectors. Magnitude of vectors. And think about components if you have to. Okay, in this case, we don't have to think about components because they're pointing in the same direction. There's no real angles involved. Okay, so what's E1 going to equal? E1 is K Q1 divided by R squared. So K is 9E9. R1 is, it looks like 5E negative 3. That's just, 0.005 meters or 5 millimeters, right? We're good? Oh my God, just kidding. You're going to let me get away with that. Q is what's supposed to go up here. God, 3 E negative, what's micro? 6. We'll need to fix that in editing. 3E negative 6 and divide by the distance squared. That is 5E negative 3 squared. Okay, typically electric fields pretty large. Like, don't be surprised if you get a big number. Lizzie, question?
Yeah, you said electric field warps the space around it. Is that like a trampoline?
Yeah, that's usually the analogy that teachers and books offer, which is the idea that, and usually we think about mass. So basically, picture a giant trampoline in your backyard or something, and drop a bowling ball in the center of it. The bowling ball doesn't just cause it to dip right in the middle, but it actually changes the slope of the entire trampoline tarp, right? The heavier the mass is, then the more concentrated it is. That's how we imagine and envision gravitational fields warping space. By the way, a black hole, and this is just kind of crazy, would be like ripping the trampoline. Because it's such a dense amount of mass that it would just like be stuck straight on the ground, like actually destroying the trampoline. Yes?
So are there special like electric black holes?
Like where the charge is so strong that not even charge could escape? Yeah, I mean, I feel like that's not... a black hole has to do with like light. Like it's so strong that not even light can escape from it. So I don't know if you'd say that the magnitude of charge is so strong that it actually has some kind of electrostatic like attraction to light. Because light is supposed to be massless and chargeless. It's a photon. Okay, so yeah, I don't know what the analogy of that would be. If you could have such a concentrated amount of charge that something unexpected would happen. I'm not sure. It's something good to think about. Good thought experiment. Okay, so doing a little math here. I got E negative 3 squared on the bottom. That's basically going to cancel that E to the negative 6 on top. I have 9 times 3, that's 27. 27 over 5. I believe that's 5.4. And then I have E to the 9th. I don't know why I just switched to blue. God, I screwed up my color scheme. Ah! What? Oh, I know what I forgot. I didn't square that 5, so it's supposed to be 25. So it's 1.08?
Yeah.
It's Monday, Jamie. Cut me some slack. 1.08, what are the units? Newtons per coulomb, because that just looks awful. Jamie, this is all your fault. 1.08 E9 newtons per coulomb. Just kidding, Jamie. E2, Brute. E2 is 99. We're going to party like it's 99. And then this charge is 6. Oh, notice something, please. 6 names. Do you notice that I neglected the negative sign in the charge? I'm just figuring out magnitude. Why? I've already dealt with the negative sign. The fact that the charge is negative, I use that to draw my vector, right? So I'm ignoring the negative signs, just like we were talking about doing for Coulomb's law. Ignore the negative signs. You've already figured that out, factored it in when drawing the vectors. So divided by 0.3, so 3e negative 3 squared. Well, unless I screw this up, Jamie, that cancels with that cancels with that. So I basically end up with 6E9. Yeah?
Sure.
Yeah, is that what you got? Jamie?
Let me know.
So my final net electric field, add these two together, I just get 7.08 E9 newtons per coulomb at 180 degrees. Booyah. Box it. Take it home. Put it in your refrigerator. Take it out of your refrigerator tomorrow. Smell it first to make sure it hasn't gone bad. Put it in the microwave. Heat it up. Get out your chopsticks. It's more fun to do with chopsticks. Boom. Delicious, tasty, delectable, delightful treat. What I want you to do is I want you to try to do the second problem on your own. It's harder. Good luck. Is this thing battery die yet? Okay. Here we go. We have an equilateral triangle. I'm going to call this guy 1. I'm going to call this guy 2. And they're both positive. Step 1, draw the vectors. So from charge 1, it's going to point that way. That's E1. And then from charge 2, it's going to point that way, E2. However, both charges are equivalent, and they're the same distance away, which means E2 and E1 are going to be equal. They have an equal magnitude. E2 has the components this way and up. E1 has components to the right and up. Those components, this guy over here, I hope you realize that's 60 degrees. This angle is 60 degrees because we have an equilateral triangle. Corresponding angles. Hopefully that makes sense to you. This component over here is E2 sine 60. This one over here is E1 sine 60. The x components, just by looking at it, the symmetry of the problem, they are going to cancel out with each other. Okay, the x components cancel. They're going to cancel, so that cancels with that. And we're just going to have the y components left over. The y components are both pointed straight up. We don't even need to hop in the PT Cruiser or use inverse tangent. Our net EField is going to point straight up at 90 degrees. Our answer, our net electric field, is going to be 2E, I'm just going to call them E1 because they're both the same when I add them together, sine 60. Okay? Sine 60 is root 3 over 2. So my answer is root 3 times E1 at 90 degrees. That's my answer. Of course, what is E1? E1 or E2, either way you do it, is, so we have root 3 times 9E9, that's K, times Q, 2E negative 6, divided by R squared, that's 2E negative 3 squared. See, that cancels with that when you square it. 2 squared is 4, 2 over 4, that's 2 on the bottom, so I get root 3 times 9 over 2, E9. I guess we could maybe just turn it all into a decimal, or we could just say, if you want 4.5 root 3, I'll just turn it all into a decimal. 4.5 times root 3 equals 7.79 E9 times 10 to the negative 9 times 10 to the 9th newtons per coulomb at 90 degrees. Boom. Delicioso. Okay? Good?
Yeah.
It's going to take some practice. Let's do this one down here. Find the net force acting on particle A. This is going to be maybe a little bit harder. Actually, this is definitely going to be harder, but a good practice problem. Okay? Net force. Now we're not talking about EField because we actually have a charge sitting there. How many forces are acting on particle A? Dose. The first one comes from B. Which direction is it pointing? Away from it. It's being repelled, right? Call that FAB. Okay, Mr. FAB. And then from down here, AC, which way is that guy pointing? I'm going to draw on the hypotenuse of that triangle there. It's going to point, boom, like that. FAC. Okay. What do we do next? We need to find the components of FAC. To do that, there's a couple things that we need to know. What is this angle? I need to know that angle. It's a hard problem. You got to use all different kinds of math. It's the same thing as this angle, right? So I have, what's the hypotenuse of this triangle? It's a 0.03, 0.04, 0.05 right triangle. You can use Pythagorean theorem, but 3, 4, 5, boom. Okay? Instead of actually even calculating this angle, what is sine of that angle equal? 0.0, opposite over hypotenuse. It's just 3/5. What's cosine of that angle equal? That's really all I need. Okay, I don't actually need to figure out what the angle is. You can if you want. You can just do inverse sine, inverse cosine, inverse tangent, whatever floats your boat. But I don't need it. Okay? So I want to separate this into components. My components of FAB, that's pretty easy. I just have, and I'll call it negative, just pointing to the left. I just have negative FAB, comma, 0. And my components of FAC, I have negative FAC, cosine theta, and positive FAC, sine theta. You guys cool with that? I'm going to add the components together. This is a harder one. I have some angles to resolve, some vector components to figure out. So let's just do, what does FAB equal? It is K, so 9E9, times Q1, that's 10 negative E negative 6, times 10E negative 6, divided by 5E negative 2 squared. On top, I get, let's see, 9 times 10 times 10, that's 900. And then E negative 3. On the bottom, I have 25 E negative 4. 25 goes into 900, I think, 36 times. Is that right?
Yeah.
Cool. E to the negative 3 over E to the negative 4. How good's your mental math? I'm lapping you guys right now.
7. Oh, just kidding.
Yeah, that's kind of weird that I put E1, right? Let's just call it 360. 360 newtons for FAB. What about FAC? FAC? Oh, you guys! I screwed it up. You know what I just did? That was FAC. Because I used 0.05. So I'm just going to change that. That was FAC. I used 0.05. I was testing you guys. And now I got to do FAB. And again, I screwed up my color scheme. Gah! 99, 10. The numerator's all going to be the same. E negative 6, 10, E negative 6. Only the denominator's different. 4E negative 2 squared. So I get 900 E negative 3 over 16 E negative 4. 900 divided by 16. So I get 562.5 newtons. Okay? Yeah, now let's just rewrite this whole thing here. Okay? So FAB, so I have, it becomes negative 562.5 comma 0. And then for FAC, what? Yeah. Didn't I? Yeah. See how I changed it? Well, I don't know. I mean, I'm screwed up way too much time. FAC cosine theta, so FAC is 360. 360 times, so negative 360 times 4/5. Let's see, a fifth of that's 72. 72 times 4 is 144. 288. Calculators are for suckers. So I get negative 288. And then I get 360 times 3/5. So I go
216.
208. No, 206.
216.
72 times 3. 210. 216. There you go. I'm a sucker now. Okay, now I'm going to add them all together. So for my components of my net force are 7, 8, 840, 850.5.
Really?
850.5, negative 850.5, comma 216. Okay? If I were to graph this, negative 850.5 that way, 216 up. I need to hop in my PT Cruiser. And I get a magnitude of 877.5 newtons. Work on my inverse tangent. And I got, this angle is 14 degrees, 14.25 degrees. Of course, I want to respect the x. I'm going to subtract 180 for it, and I get at 165.7 degrees. Boom. Okay? Any questions? Hard problem. A lot of steps. Okay? Staircases have a lot of steps, and you only have some problems getting up those. Right?
Take the elevator.